Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right, good morning, everyone. So today is the continuation of Monday's exotic option. The first option we're going to look at is our Asian options. So basically, there are two types of Asian option. The first one is called the Asian average price option, right? For example, the way how average price option works is that instead of having the final spot price subtract the strike price to work out the payoff on the call option, we're having an average of the spot price, that acting as the final spot price. Then the average price minus the strike price give us the payoff on the Asian price call option, right? And the same thing goes to the put option. So instead of having the strike price minus the final spot price, we're having the spot price minus the average spot price. So that gives us the payoff on the put option, right? So on Monday, I motivate the reason why people use Asian option is because it's more suited for corporation hedging purpose, right? So for example, I said, suppose a US corporate treasurers expect to receive a cash flow of 100 million of Australian dollars spread evenly over next year from the company's Australian subsidiary. And the corporate treasurers is more likely to be interested in the option that would guarantee the average exchange rate realized during the year that is above certain level, right? So if that's the case, then the average price put option can achieve this more efficiently than your regular put option. So that's what we have talked about on Monday. And the second type of Asian option is Asian average strike price option, right? So the way how the strike price option works is that instead of having the final spot price minus the strike price K, we have the final spot price minus the average spot price, right? So basically, the average spot price is acting as the strike price in the Asian strike options. And the same thing goes to the put. So instead of having the final spot price, instead of having the K minus the final spot price, we're having the average spot price minus the final spot price to work out the put. So basically, the average strike option can guarantee the average price paid for an asset over a period of time is not greater than the final price. So that's for the average strike call. Alternatively, it can guarantee the average price received for an asset over a period of time is no less than the final price. Okay? So that's some of the recap about Asian options. Now let's have a look at this little question here. So the question says, suppose that the C1 and P1 are the prices of a European average price call option and a European average price put, with the strike price of K, maturity time T, right? And then the second part says, suppose that C2 and P2 are prices of European average strike call option and European average strike put, also with maturity in time T. C3 and P3 are the price of regular European call and regular European put with the strike price K and a maturing time T. And the question asks us to show that we need to establish this relationship. So what kind of relationship? C1 plus C2 minus C3 equal to P1 plus P2 minus P3. So to prove this is quite straightforward because we know the payoff from the average Asian price option, and also we know what the payoff look like for the average strike Asian option, right? And also, for sure, we know what is the payoff from your regular European option. So maybe we can write down, so the starting point is let's write down the payoff for each type of the option, right? Then we can manipulate the equation based on the end goal here, right? So we have our end goal in mind, so that's what we try to achieve at the end. So at the beginning, let's write down the payoff from each component. So here it is. We just did a quick revision of what the Asian options payoff look like. So remember, the C1 is your average price option, right? So that's the payoff from your average price option. So that's the average price minus strike price for call. And the second set of options are average strike option. So average strike option for both call and put. So instead of having the strike price, we have the final spot price minus the average spot price, right? And the last one is something we're really familiar with, which is your regular European option. Simply the final spot price minus the strike price. Okay, and the same thing goes to put options. So the first is the average price put, second is your average strike put, and lastly is your regular put. Okay? Now, let's have a look, what do we try to achieve here? Maybe one thing we can do, for example, if you rearrange this P1 to your left-hand side, you realize it's C1 minus P1, right? So you can try to work out what's the C1 minus P1 look like. So C1 minus P1, if the call option has a payoff, that means the price is above the strike, right? So because the way how this payoff is represented is the maximum value between either in the money or we don't exercise, right? So that's basically what this bracket tells us. Now, if the C1 is in the money, if this average spot price is larger than your strike, then your put option cannot be in the money at the same time. So that's the rationale behind it. So let me say this again. So if you want to have this Asian price option, call option, to be in the money, then the Asian price put option cannot be in the money. Sorry, excuse me, can you guys stop talking in the back? Yeah. So let me say this again. So basically, if you want to have this Asian call price option in the money, then the put option cannot be in the money at the same time. So that's why we have nothing coming from our Asian price puts, okay? So that's just your Asian call price option minus nothing here. Then what you end up with, C1 minus P1 is simply the payoff from your price call option. Okay, so same rationale goes to the average strike option. So C2 minus P2, if you want the call option to be in the money, then the put option cannot be in the money, right? So all you end up with is the payoff coming entirely from the average strike call. So that's what we're getting here is ST minus the average spot price, right? So that's coming from the average strike call option. And lastly, we know what to do with the regular option, right? So the regular call option minus regular put option, again, if the call option is in the money, the put option provides you with nothing. So you end up with the payoff from the call option. Okay? So this is our end goal. Sorry, this is our end goal. This is what we try to prove here. So we'll try to prove this relationship. So now we can put all of the payoff together, right? So if you're using the C1 minus P1 plus C2 minus P2, we're getting this equation here, right? So that's the payoff from C1 minus P1. That's the payoff from C2 minus P2. And you realize that the average price just cancel out. What you're left with is ST minus K, right? So ST minus K, we know what ST minus K is. ST minus K is simply the payoff from your regular call option minus regular put option, right? So we can prove that this relationship must be true, which is C1 minus P1 plus C2 minus P2 must equal to the payoff from your regular call minus regular put, right? So we prove that relationship is true. Then it's just a matter of rearranging this equation. We prove what the question is asking for. We prove this relationship, which is C1 plus C2 minus C3 equal to P1 plus P2 minus P3. Okay, so the first example is nothing difficult. The real thing that this question is testing you is whether you're familiar with the payoff from the average price call put or the average strike call and put, right? So if you remember the payoff, then nothing's difficult. It's just manipulating the equation and get what we try to achieve here, right? So that's with the first example. So any question with the first example? Quite straightforward. Okay. Okay, another type of interesting exotic option we learned from Monday's lecture is something called chooser option. Okay, so basically chooser option has the feature that after a certain period of time, the holder can choose whether this option to be a call option or to be a put option. All right, so just imagine a timeline. Imagine the chooser option would mature in T2, okay? So T2 is the maturity for the chooser option. And let's assume halfway through this holding period, let's say T1, so T1 is right in the middle, you can make a decision on whether or not you want to get into a call or get into a put. Okay? So let's assume the decision is made in T1. All right? Okay, so you would observe the most updated spot price based on T1. Then you make a decision. You choose the higher value between either the call or put. So that's how the chooser option work. So once you made a decision, now let's assume if you get into a call option, then the call option will last until T2. So what is the maturity for this call option? The maturity for this call option is simply T2 minus T1, right? The difference between the T2 minus T1. Okay, so we're just going to bear that in mind. Again, this question just testing your knowledge about the payoff from the chooser option and nothing more difficult. So the question says, the option underlying the chooser option are both European and have the same strike price. So the part one says, suppose that S1 is the stock price at T equal 1. Remember, T equal 1 is the point in time where we made a decision, we made our mind, we want to get into call or put, right? So K is the strike price, T2 is the maturity for the chooser option, and I is the risk-free rate, Q is the continuously compounded dividend yield. And the question says, using the put-call parity to derive a valuation formula in the expression of the put option, in the expression of P. Okay? So at first glance, you probably don't have a clue to do this question. Maybe you can start with something that we're really familiar with, which is the put-call parity, right? So what I'm going to do is I'm just going to grab the regular put-call parity equation. So basically, what the put-call parity try to tell us is this equality must be true, which means on the left-hand side of the portfolio, if you have a call option and the present value of the strike, it must provide the same payoff as if you have a put option plus 1 unit of underlying asset, right? So that's what the put-call parity try to tell us. Now, having those information, and let's think about the last sentence said, we want to have a valuation formula in the expression of P. So when we look at this put-call parity, we know how to do that, right? So in the expression of P, simply rearranging this equation and express the put-call parity, so basically having the put option on the left-hand side and everything else on your right-hand side. We know how to do that. So if we put the put option on the left-hand side and everything else on the right-hand side, what we're getting at is C plus the present value of the strike minus the S0. So that's how we express the put option using the put-call parity with the regular options. However, we're dealing with the chooser option here, right? So we need to do some modification on that expression. So what modification we need to do? First of all, we need to replace all of the T with the maturity of the option, right? So the maturity, as I mentioned before, the maturity for the option is really the difference between T2 and T1. Because before T1, the chooser option doesn't have a nature, right? The chooser option is neither call nor put. It doesn't have a nature. So you made up your mind whether it's a call or put in T1. So that's when the nature of the option is determined. And then the option would last until T2. So the maturity must be T2 minus T1, right? So the difference between T2 and T1. So we need to replace all of the T with T2 minus T1. That's the first thing we have to do. And that's easy. So for example, with the present value of the strike, instead of having K times the e to the power of minus RT, we're having this expression here, right? And the second thing we need to do is, because we're dealing with an asset that pays a dividend yield, and we know how to deal with the asset that pay a dividend yield in prior weeks, right? So all we did is simply removing the dividend yield from the current spot price. We can do that. So we're going to use the S times the e to the power of minus Q, then times T2 minus T1. Why is S1? Because S1 is the spot price in T1. T1 is the point in time where we made a decision, right? So that's the starting point for our option. So that's the starting or the initial spot price, if you like. So that's the spot price in T1. Okay, so we're going to use this expression to replace S0 in our put call parity. Okay, so we just did two modifications. Well, if we do that and we rearrange the equation, we get expression for the put option, right? So the put option can be expressed as this. All right, so once we have done that, remember the payoff for the chooser option is the maximum value of either the call or the put, right? So that's maximum bracket C or P. Okay, so that's the say, that's the call option, and the put option can be expressed in this equation here, right? So the put option can be expressed in this equation, which we just derived, and then we can make this payoff look more compact, which is look more tidy. So one thing we can do is we can get rid of the C first, so we can move the C outside. So if you move the C outside, we have 0, and then we have K, the present value of the K, minus the spot price without the dividend yield. Okay? And the next thing we can do is we can single out e to the power of minus Q bracket T2 minus T1, right? Because that's the common component in this thing here and that thing here. So we can single out the e, so we can single out e to the power of minus Q times T2 minus T1 from this equation. Now, if we do that, we can actually move that outside of the bracket, right? So we're having a more compact expression of this equation here. So this equation is identical to the first equation, right? So we have the call option plus the e to the power of minus Q times T2 minus T1 and a maximum of this. So if we do that, we can have an interpretation about chooser option payoff. So basically what the chooser option is all about is that chooser option can be decomposed into two components. The first is that it's a call option with strike price of K. And then is this much quantity of put option with the strike price of K times the e to the power of minus the difference between R minus Q, then times T2 minus T1. Right? The reason why we can interpret like this is because this is essentially the payoff from a put option, right? And that's the quantity of that put option. And then we have a call option here. The call option has a strike price of K. So in other words, the chooser option is really comprised of a call option and certain amount of the put option. Okay? So that's the part one of the second example. Any question with this one? So let me summarize. The first step we did is to pull out our regular put call parity equation. Then we recognize that we need to do some modification on this put call parity. So we replace this with the present value of the strike. Then we replace the spot price with this equation here. Then we derived a payoff equation for the chooser option, right? And then we kind of decomposed this payoff into two components, and we recognize that what chooser option really comprised of is a call option and certain amount of put option. Any question on this one? All right, then it's part B of this question is quite similar. So part B says, using the put-call parity to obtain expression for C instead of P, right? Again, our starting point is our put-call parity. Then we need to do some modification on this put-call parity, and we're having the C on the left-hand side, and everything else goes to the right-hand side, right? So we're just rearranging the equation, so that's essentially still the put-call parity. And then what we can do is we can substitute this equation for C, right? So we substitute this equation for C, and we're having the P here. Again, one thing we can do is we can subtract the P from the bracket, so what we have is 0, plus this equation here, right? And then we recognize on the right-hand side of the equation, there's a common component, which is e to the power of minus q times t2 minus t1. And we can single out that. So we can single out e to the power of minus q times t2 minus t1 from this right-hand side of the equation. And we can reorganize that outside of the brackets. So basically, we have this expression here, which is quite similar to the part 1 question. And then, again, we can make an interpretation about chooser option payoff. Basically, the chooser option payoff is really comprised of, first, is a put option with strike price of K, and certain amount of the call option, so this quantity, right? The quantity is expressed as e to the power of minus q times t2 minus t1, and with the strike price look like this. Okay, so pretty similar to the part 1. It just this time we express C in this equation here. Then we substitute into the chooser option payoff function. Any question with the chooser option? All right. Okay, so let's have a look at the third question. Third question is quite interesting. So the third question says, suppose the strike price of American call option on a non-dividend paying stock is growing at rate of G. So we know that in your regular American call option, the strike price is fixed, right? But here it says the strike price change over time, and the strike price is growing at a growth rate of G. And the second part of the question says, show that if your growth rate on this strike price G is less than the risk-free rate R, this call option should never be optimal to exercise early. So how do we prove that? So let me say this again. So we're having a call option, American call option, and its strike price is growing over time, and the growth rate is G, right? Then we have our risk-free R, and the question says, assume if the growth rate is less than the risk-free R, then it's never optimal to exercise this American call option early. Okay, so how can we prove this? So first of all, we have to ask the question, what is the terminal value for the strike price? What is the terminal value for the strike price? Given that the strike price is growing at the rate of G, then the terminal value of the strike price must be K times the e to the power of GT, right? So that's what the strike price look like at the terminal point, right? If we simply let it grow, it look like this. Okay, if that's the case, assume if we want to exercise this American call option at maturity, then we need to pay the strike price, right? So once you exercise the American call option, if American call option is in the money, if we want to exercise it, once you exercise it, the next thing happen to you is you need to pay the strike price. So we want to get ourselves prepared for the scenario that we exercise the call at terminal point. How can we get ourselves prepared? Perhaps we can save up some money today, right? We can save up some money. How much money we need to save up? That's how much we need to pay in time t, right? Now, if we discount back this strike price back to the present, that's how much cash we need to set aside. That's how much cash we need to deposit in a bank account, and so that we would have enough money to pay the strike price. So in other words, the present value of the terminal strike price can be expressed as this. All I did is to discount this terminal strike price back to the present. The way I discount it is times the e to the power of minus RT. Okay, so that's all I did. Now, the more compact way to rewrite this is k times the e to the power of gt minus RT. Okay, so this is the present value of the terminal strike price. Just bear that in mind. Okay, now we have the present value of the strike. What we try to demonstrate is that it's not optimal to exercise in a point in time which is earlier than the terminal point, right? So we know the terminal point is time t. Let's find a point in time which is halfway through the holding period, okay? So let's assume starting from today, time equals 0, and halfway through the holding period, we end up to the point of tau, t equals tau, all right? So this is what I said here. Assume some time has passed. In time tau, so time tau is in the middle of the initial point, and the terminal point is right in the middle, let's say. And cash amounts that we saved in the bank accounts, remember we save up some cash today, the amount of cash we saved is the present value of the terminal strike. Now, that present value is growing at a risk-free rate, right? We're saving in the bank accounts, and it will grow with the length of tau. So that's how much the cash that we're saving in the bank grow to the point of tau. So that's the present value of the terminal price times the e to the power of r tau, okay? So if we do that, we can write this equation like this, right? Then I try to show that this is strictly less than the strike price in the point of time tau, okay? Now, if I want to show that, I try to reorganize this equation more look like the strike price, okay? So let me say this again. So because I try to prove that it's not optimal to exercise this American call early, so what I try to demonstrate is that the money I put in the bank account is not sufficient for me to pay the strike price in the point of tau, right? We know in the point of tau, our strike price would simply look like k times the e to the g tau, right? So that's how much the strike price have grown to. Now we try to reorganize this equation, try to look a lot more like the strike price. Then we need to prove that the money we saved in the bank accounts is strictly less than the strike price that we needed to exercise the American call at the point tau. Okay, so that's what we try to achieve here. Now, one way we can do with this equation is we can do a cheap mathematical trick, which is to plus something, then minus the same thing. Because if you plus minus, you're not doing anything to the equation, right? So I decided I try to plus g tau minus g tau here. Then we can group that together, right? We can group like this. Then we can rewrite it in a more compact way, which look like this. Okay, then we can rearrange this equation and make it look like this. And then lastly, we can try to break up a little bit. So basically, that's just k times the e to the g tau times the e to the power of minus bracket r minus g times t minus tau. Okay? So once we can derive this equation, let's analyze what is this all about. So basically, the first half of this equation is our strike price, right? We established this already because the strike price is growing at a rate of g. So at a point in tau, this is how much the strike price was, right? So that's your strike price. And bear in mind, in this question, the question says the g is less than the risk-free rate. Well, if the g is less than the risk-free rate, then r minus g must be a positive value. Everybody can agree on that, right? So if the g is less than r, that means the risk-free rate is larger than the growth rate g. So this bracket must be a positive value. And then, because the tau is halfway through the holding period, so the t minus tau also must be a positive value, right? So that's the two positive value. That's the product of two positive value, and we have a negative sign in front of that, which means we have a negative power here, right? If it's negative power, that means we are discounting the strike price, which means the amount of cash that we receive in the bank accounts must be strictly less than the strike price in time tau. Does that make sense? So this is your strike price, and we establish this two brackets product must be a positive value, and there's a negative sign in front of that. So basically, this equation must be strictly less than k times the e to the g tau. All right? In other words, the amount of money that we receive in the bank accounts to the point of tau is not sufficient for us to pay the strike. If it's not sufficient for us to pay the strike, then it's never optimal to access this American call option early. Does it make sense? So the most optimal way is to wait until the cash balance in the bank accounts fully grow to k times e to the g tau. Then we can exercise this American call option, and we have sufficient amount of money to pay the strike at a terminal point. Okay? So basically, the payoff can be written as this. So we established that early exercise is not optimal. Does this question make sense to you guys? Any question with example number 3? So let me summarize what I did. We are given American call option, which is not the regular American call option because the strike price changes over time. And the first step we did is we'll try to figure out how much money we need to save up today in order to exercise this American call option at maturity. So the way we did that is to discounting the terminal strike price back to the present. And we kind of argued the present value of the terminal strike must be the amount of cash we need to start saving today. And then, in order to prove that it's not optimal to access this American call option early, we kind of arbitrarily choose a point in time, which is halfway through the holding period, which is tau, right? So tau is in the middle of the holding period. And we checked our cash balance in point in tau, and we realized that the cash balance that we save in the bank account in time tau, is actually less than the strike price in time tau. Then we argued that if our money is not enough to pay the strike in time tau, then it's never optimal to access this American call option early. And then we argued that if we simply let the cash balance fully grow to the strike price in time t, then we would have sufficient money to access the American call. So the best way to deal with this American call option is simply wait until the maturity t, wait until our bank account have enough cash for us to access this American call option. All right? So that's what we did. So if there's no question, I'll just move on to the binary option. Okay? So what is binary option? So basically, there are two types of main binary option here. So the first one is called cash or nothing call option. Okay, so we kind of dealt with cash or nothing call option. So when we talk about the Greek letters, there are two examples towards the end of the lecture. Actually, one of the question, I think I remember the second question is kind of like a cash or nothing call option. So the way how the cash or nothing call option works is that this call option would pay you nothing if the underlying asset price end up below the strike price, right? And then if the underlying price end up above the strike price, this option would pay you a fixed amount of cash Q. Okay, and remember when we did Black-Scholes formula back in week 6, I give you guys intuition behind the equation, right? The intuition was the ND2 is the probability that determines the spot price get above the strike price. Remember? So if you go to your week 6 lecture slide, I give you guys some intuition behind the Black-Scholes pricing equation. So here it is, intuition on Black-Scholes formula. So when I talk about the way I talk about D2 is that what is the probability? So the ND2 tells us what is the probability that the call option finishes in the money. In other words, ND2 tells us what's the probability that the asset price gets above the strike, right? So ND2 gives us that probability. If that's the case, then the value of this cash or nothing call is simply the present value of the cash amount times the probability that you will get that cash, right? So ND2 tells us how likely the spot price get above the strike. So in other words, the present value of the cash amount Q times the probability you will get that cash give us the value on this cash or nothing call option. Okay, then we have cash or nothing put. So basically the cash or nothing put works is that the option would pay you a fixed cash Q if the spot price gets below the strike. Okay, so that's just N minus D2, right? N minus D2 give you the probability the asset price finish below the strike price. So the value on this cash or nothing put is simply the present value of the cash amount times the probability that the price will get below the strike. And that gives you the value on this cash or nothing put. So that's the first type of binary option. And the second type is called asset or nothing call. So as the name suggests, asset or nothing call is that this option would pay you nothing if the spot price finish below the strike price. And it will pay you the asset, so basically it will pay you the asset price if it end up above the strike. Okay? So how do we value this asset or nothing call option? Well, there are two things we need to determine. The first thing is that still as before, how likely our spot price finish above the strike. So that's one thing we need to worry about. And the second thing is that if that happens, how large is our asset price? In other words, how large is our expected asset price, right? So we need to determine two things at once. So the ND1 in the Black-Scholes equation give us that probability, so like conditional probability. So basically what ND1 times the asset price tell us is the expected share price at time t given conditioning on that the share price finish above the strike. So there are two things going on here. So the way we value this asset or nothing call is simply the spot price times the ND1, because ND1 taking into account of the probability the asset finish above the strike. At the same time, it gives us the expected asset value in time t. So ND1 is the one we need to use to value this asset or nothing call. What about asset or nothing put? So basically, asset or nothing put gives give you nothing if the asset price finish above the strike. If it finish below the strike, then they would pay you the asset, which is the asset price. So that's simply the spot price times n minus d1. Okay? So we need to bear that in mind. Now, the difficult thing is when you read the question, you try to figure out which side you are. So are you getting the cash or are you getting the asset? So that's the tricky part. We can do one example together, then we can try to figure out whether we are getting the cash or we're getting the underlying asset. So the other thing I want to mention is that this look very, very much like your regular European co-option equation, right? So if we put the regular European co-option equation side by side with this one, you'll realize that they look very similar. Okay? So actually, we can interpret this equation. The way we're going to interpret this equation is that a regular European co-option is really a long position in an asset or nothing co-option. So that's your payoff from the asset or nothing co-option. And a short position in the cash or nothing co-option, right? So that's the value of cash or nothing call. So basically, the regular co-option is a long position in asset or nothing call, and a short position in the asset or nothing call. Sorry, cash or nothing call. And similarly, we can give intuition on the regular European put option. So a regular European option is really a long position in a cash or nothing put, and a short position in the asset or nothing put, right? So that's just some interesting fact. So let's have a look at this numerical example here, and let's try to figure out whether we're dealing with an asset or nothing call or cash or nothing call. So this question says, what is the value in dollar terms of a derivative that pays off 10,000 sterling, pound sterling in 1 year, provided that dollar sterling exchange rate is $1.50? So basically, we're spending $1.50 US dollar to buy 1 unit of sterling. And the current exchange rate, the spot rate, is 1.48. So basically, we're spending $1.48 US dollar to buy 1 unit of sterling. And what we're told is the dollar and sterling interest rates are 4% and 8% respectively. The volatility on the exchange rate is 12% per annum. Okay, so how can we value this binary option? So first of all, let's think about from dollar holder's point of view, right? If you are an investor that you are holding the dollar, let's read about this payoff. Okay, so the value, this derivative would pay you 10,000 sterling in 1 year, provided the spot rate would above 1.5, right? So first, one thing we're sure of is this is a call option, because when the spot price finishes above the strike, it gives you a payoff, so it must be a call option. But the question is whether this is cash or nothing call or asset or nothing call. Okay, so if the dollar sterling exchange rate gets above $1.50, we will be paid in the form of a foreign currency, right? We'll be paid in the form of sterling. Right, so I'm talking about this from dollar investor's point of view. So sterling to the dollar investor is kind of like an asset, right? Because dollar to the dollar investor will be cash, then sterling to the dollar investor's point of view must be the asset. So if we're thinking this entire question from dollar investor point of view, then this is an asset or nothing call option, right? Because you'll be paid 100,000 sterling. Okay, if that's the case, then we know how to value the asset or nothing call option, because we learned earlier the asset or nothing call is determined by this equation here, which is simply the spot price times ND1. So the first thing we need to do is to work out what the D1 is. Then we need to find the corresponding probability for D1. Okay? So we have everything we need to calculate D1. We have the spot price, and then we have the strike price. So spot price is the $1.48, and divided by the strike price, then the domestic rate, because we're thinking this from dollar investors' point of view, so the domestic rate is 4%, and foreign rate is 8%. Right? And that's your variance divided by 2. The maturity is 1 year. So we work out the D1 value is minus 0.38. Okay? Then you go to your statistical table, you find that the probability is 0.35 associated with that D1 value. Then because we're valuing this in the dollar term, so read the question carefully. The question tells you you must value this derivative in the dollar term, right? So we need to convert this asset using the exchange rate. So the exchange rate is 1.48. So that's our spot exchange rate. So we convert that sterling into dollar, and we discount it. So, and also we're removing the effect of foreign risk-free rate, right? So the 8% is your foreign risk-free rate. We're removing the effect of foreign risk-free rate, and that times ND1 give us the price of this derivative from dollar investors' point of view, right? So from dollar investor point of view, this is asset or nothing call option. Well, we can approach this question differently. We can approach this question from sterling investors' point of view, right? So dollar to the foreign currency, so if the dollar is the foreign currency, if we view this derivative from the sterling holder's point of view, what we're doing here is we're kind of spending this much sterling to buy 1 unit of dollar, right? Because sterling is worth more than $1. So we're spending 0.67 sterling to buy 1 unit of dollar. Okay? So if the dollar sterling exchange rate get above 1.5, in translation to sterling investors' point of view, is that the exchange rate gets below 0.67, then this derivative would provide a payoff. So that sounds a lot like a put option, right? Because from sterling investors' point of view, if the spot price gets below this, then this would make a payoff. So that sounds a lot like a put option. And if that happens, then the sterling investor will be paid in the form of sterling. And the sterling to sterling investor is cash, right? Because sterling to sterling investor is your domestic currency. So the sterling investor will be paid in the form of cash. So it's safe to say that from the sterling investor's point of view, this derivative is a cash or nothing put, right? Cash or nothing put, because the investor will be paid in a fixed amount of sterling. So to sterling investor is a cash. And we know how to value put options. So the first thing we need to do is to work out D2. And remember, the spot price you're using in this second part of the question is 1 divided by 1.48, because this is from sterling investors' point of view. And the strike price is 1 divided by 1.5, right? And then this time the domestic rate is 8%, and the foreign rate is 4%. Foreign rate is the US rate. So we work out D2 is this value here, and we go to our statistical table, find the corresponding N minus D2. Okay? So once we do that, we just need to use the fixed payoff that discount back to the present times N minus D2. And so that's the value in the sterling currency, right? Because the question is asking in the dollar amount, so we need to convert this sterling value using the spot exchange rate, and we convert back to the dollar value. So that's worth 4,782, which is same answer we get as the part 1 question. Does it make sense? So I think the tricky part with this question is to think whether we're standing in the point of view of dollar investor or are we standing in the point of view of sterling investor. And then we'll try to figure out the payoff structure, right? So from sterling investor point of view, this is the put option. And from dollar investor point of view, this is the call option. Then we'll try to figure out if the option becomes in the money, are we paid in the form of cash or are we paid in the form of asset? Then once we figure that out,